Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. The lecture is on basics of time series analysis. And for this lesson, I will introduce estimation approaches for seasonality. This slide provides a snapshot of the basic modeling of time series. For the simplest time series analysis, the response data are Y, T, the time-varying observations where T is the time index, for example, day or month. In order to account for trend and seasonality or periodicity, we decompose the time series into three components, MT, ST, and XT, where MT is the trend, ST is the seasonality, and XT is the time process after accounting for trend and seasonality. XT is often assumed to be a stationary component. Most classic time series models assume that the time series process is stationary, and thus we need to first estimate the trend and the seasonality components, subtract them from the time series YT, then further model XT. In this lesson, I'll describe common approaches for dealing with the seasonal component. Not all time series have a trend, but for those which do, we'll need to correctly account for seasonality. In the basic time series model discussed in the previous slide, seasonality is an additive component and can be estimated from the detrended data if there is also a trend component. We can remove the trend using two approaches: estimation of the seasonality and remove it, or differencing the data which directly removes the seasonality. To estimate the seasonality, we can use a seasonal averaging or use parametric regression in two ways. First, we can fit a regression model where each of the seasonal group, for example, month of the year, is specified as a dummy variable in the model. If the periodicity of the seasonality has many seasonal groups, we fit many regression coefficients using this approach. Second, we can use a cosine sine function to fit the predicting variables, where the predicting variables are the cos and the sine functions for different frequencies. The first method is very simple. It takes all time series values corresponding to each seasonal group K from 1 to D and averaging them to get the WK. Note that here D is the periodicity or the number of seasonal groups. For example, if the seasonality is monthly, then D is 12, and one seasonal group corresponds to 1 month. Because we have that the sum of the seasonal effects ST is equal to 0, the estimated seasonal effect for ST is WT minus the average across all effects. One way to perform the simple averaging is through a regression model where each seasonal group's mean is estimated via an ANOVA type model as presented in the next slide. A linear regression model approach to estimate the seasonal effects ST is to consider an ANOVA type of model where we group the data by seasonality group. If the periodicity is D, then we have D seasonal groups or effects. Thus, we treat seasonality as a categorical variable. To fit such a model, we need to set up indicator variables or dummy variables that indicate the group each of the data point belongs. When fitting categorical variables with D groups, we only include D-1 dummy variables if the model has an intercept. Thus, this approach reduces to estimating a linear regression model. This can be convenient since we have a trend. We can estimate the trend and the seasonality in one regression model. But the previous model can have many predicting variables. This regression model can have many predictive variables, particularly if we have multiple seasonalities, for example, month and week of the year, and or the periodicity D is large. For week of the year, we will need to have 52 different dummy variables, for example. An alternative approach to using linear regression without having many regression coefficients to estimate is to use a cosine sine model. In this approach, we assume a cosine curve for the seasonality specified by three parameters: the amplitude, which is how high or low the curve will go, the frequency f, which is the inverse of the periodicity of the seasonality, and the phase, which sets the arbitrary origin on the time axis. The only known parameter in this formulation is f, since it is provided by the periodicity of the seasonality. The cosine curve is thus inconvenient for estimation because the amplitude and phase parameters do not enter the expression linearly. Fortunately, a trigonometric identity is available that allows reparameterization of the cosine curve as provided on the slide. Now we have a linear parameterization where beta 1 and beta 2 are the regression coefficients with the predicting variables given by cos and sine of 2 pi f. Conveniently, if the seasonality has different frequencies, for example, month and week of the year, we can use the same formulation for each of the frequencies and introducing only the regression coefficients for each frequency. Since we have both trend and seasonality, we can use the approaches discussed so far on estimation of the trend and seasonality to remove them in order to get to a stationary process. To do so, at the first step, we can obtain an initial estimate for the trend, remove it from the time series process, and the second step, estimate the seasonality. Last, remove the seasonality from the time series process and obtain an updated estimate of the trend. The method used in the step 3 can be any of the methods used to estimate seasonality, not only the averaging approach as provided on the slide. Since we use regression to estimate the seasonality and the trend, we can do so simultaneously. For seasonality, we only have linear terms in the regression model, regardless whether using the seasonal means model or the cosine sine model. However, the trend can be linear in the predicting variables if assuming a polynomial with known order, or it can be non-parametric. To combine both into one joint model, we simply use linear regression if both the seasonality and the trend are specified by linear terms, or we can use a semi-parametric model in which the trend is non-parametric, but the seasonality is added to the model linearly. Last, we can also use differencing to remove the trend and seasonality jointly. If we have seasonality or period d, the differencing operator applied to the time series yt means that we take the difference of yt and yt minus d. If we decompose further this difference, we also have mt minus mt minus d, which could also remove the trend if the trend is slowly changing. Generally, this method is recommended when the time series is observed over a long period of time to allow for differencing over long periodicity's seasonality. To summarize, in this lesson, I introduced approaches for estimating seasonality. Thank you.